In this project, we will numerically validate the data provided by the paper called CFD simulation on the effect of primary nozzle geometries for a steam ejector in refrigeration cycle. Now in this slide you can see a model of a steam ejector that we have extracted from figure 2 of the paper. Now in this slide we have brought to you the table 3 of the paper and we're going to validate the results. The present model is designed in 2 dimensions using Design Modeler software. The meshing of the model has been done using ANSYS meshing software and the mesh tab is structured. Under the General Setup tab, you can see different buttons from scales to units. By clicking on the scale, in present project, realizable K epsilon model has been used to solve the turbulent flow equation since it is more accurate than the standard K epsilon model. Now, in order to add a new material for the project, you just have to right-click on the fluid button and then click New. After that, a window will appear. In the appeared window, you either can define a material by changing the properties, or you can click on Fluent Database button and then select a new material from the available list. In this project, we had defined a new material by changing the properties in this window based on the information provided by the paper, which is available in the table 2 of the paper. By clicking on the primary inlet boundary, you can see that the type of this boundary is defined to be pressure inlet. By clicking on Edit, a new window will appear, which you can change the settings for this boundary. Now in the appeared window, in front of gauge total pressure and supersonic or initial gauge pressure, 2 specific values have been defined, which are extracted from the reference paper. By clicking on the middle ball and clicking on Edit, after that, a new window will appear. In the appeared window, under the Momentum tab, you can see that the stationary ball motion alongside with no slip shear condition is defined for this boundary. Now, if you pay attention to the report defined in this project, you can see that 3 different reports have been defined. By clicking on the Out report, you can see that in the appeared window, a mass flow rate report has been defined on the boundaries of outlet. After double-clicking on the initialization button, a new window will appear. In the appeared window, you will see that hybrid initialization method has been chosen, which means that an average is taken from different part of the computational domain, and these averages are set to be the first and initializing values for our simulation. Now in the appeared window, under the contours of section, we select our desired variable. For example, in this slide, we have selected the Mach number, which would be under the contours of velocity. After selecting this variable, under the surfaces section, we click on the zone surface. By clicking on the Save or Display button, the software will show you the contours for Mach number. Now in this contour, you can easily see the Mach number changes inside the computational domain. In order to validate and compare our results for Mach number with the paper, we have extracted a part of paper's text, and that you can see in the highlighted section. The paper mentioned that at nozzle's exit plane, the primary fluid leaves the primary nozzle as a supersonic stream with Mach number almost equal to 4. Which you can see in this contour, we have reached to Mach number of 4 in our exit section of the ejector. Now in this slide, you can see that we have brought to you the second equation implemented in the paper, which calculates the Rm, and the formulation says that the Rm is equal to mass flow of the secondary fluid over the mass flow of the primary fluid. Now in order to calculate the Rm, we calculated the mass flow rates on each of secondary and primary inlets, and we have actually multiplied this value by 2 since we had only modeled a half of the ejector, so that in order to correctly calculate the Rm value, we just have to multiply the calculated value by 2. After obtaining the value for Rm by going into the table 3, in front of D20M4 nozzle, you can see that the value of experimental Rm is equal to 0.286. And now if we calculate the error, we can see that the maximum error for our CFD simulation in comparison to the experimental data acquired by the paper is equal to 5.94%, which is lower than the amount of error the paper itself reported. Finally, the summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product.
Now in this slide you can see a model of a steam ejector that we have extracted from figure 2 of the paper. Now, a steam ejector is a mechanical device that uses an actuator fluid to suck a secondary material, and finally the actuator fluid and the suction substance are mixed together and exit from the system. Ejectors have two main functions, including vacuuming and suctioning gases as well as mixing fluids. The ejector model in the present work has a convergent-divergent structure, and inside it a convergent-divergent nozzle is located. The operating mechanism of this ejector is such that the water vapor enters the ejector as the primary fluid, and by passing through the convergent part of the nozzle, which has a smaller cross-section, it accelerates, and according to Bernoulli's law, the pressure decreases. Now in this slide we have brought to you the table 3 of the paper, and we're going to validate the results presented in this table for nozzle type D2.0M4, and we're going to compare the results obtained by the paper for RM, which goes by the name RM experimental, and the results obtained by our CFD simulation. The present model is designed in 2 dimensions using design modeler software. Due to the symmetrical structure of the ejector nozzle and diffuser, only half of the ejector is designed. The geometry consists of 2 inlet sections for flows related to the primary and secondary, 1 outlet for mixed output fluid, and an internal part as the nozzle for the primary fluid flow has been defined. In terms of geometric scales, the model designed based on table 1 of the article, so that the throat diameter of the nozzle related to the primary fluid is equal to 2 mm, and the ratio of the ejector area is equal to 90. The meshing of the model has been done using ANSYS meshing software, and the mesh type is structured. The element number is equal to 51,990. In addition to our model mesh, we have brought to you the figure 3 of the paper, where you can see the mesh used in the paper for better comparison. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com.